Okay, welcome everyone to today's TCS Plus talk, the first of our sort of quarantine edition of talks. My name is Gautam and I'll be your host today. So in case you haven't heard, TCS Plus is going weekly rather than bi-weekly in response to, perhaps the increased demand for some sort of intellectual stimulation during this unusual time. So today, well, let me not spoil the surprise of who we have today. But I'll point at some of the future talks first, that next week, 1 week from today, we have Venkat Guruswamy, who's actually I see in the audience today, but followed by a great series of speakers after that as well. Rahul Ilango is going to be 2 weeks after that. Then Ramon van Handel is going to be after that, Hua-Cheng Yu, Sepide Mahabadi, and Nathan Klein. This series of talks will take us all the way into May, in fact. So we're set. We're ready for the long haul. We're here to support you in this time of need. If you need TCS talks, perhaps a luxury at this time. But okay, I'll mention that while we're a bit full on talks right now, you can still suggest things via our form on our website. But without further ado, let me introduce today's speaker. We're very lucky to have Dana Moshkovitz, who's a professor at UT Austin, speaking to us today. Dana is an expert in limitations of approximation algorithms and PCPs, that is probabilistically checkable proofs. Especially in the latter, her work is very well known and recognized. For her work, she received the Fox 2008 Best Paper Award, as well as the Netanyahu Prize, which is awarded to the best maths PhD thesis in all of Israel as well. So yeah, we're very lucky to have her speaking today. And without further ado, I'll pass it over to Dana. Could you please share your slides?
Okay. I co-won the Netanyahu Award. They usually pick one from TCS and one from math to jointly win the best math thesis. Anyway, it's a great honor to inaugurate this Corona edition of TCS Plus. Okay, so let me start. So I'm going to talk about new work with David Zuckerman, Dean Doron, and Justin O. Dean was a joint postdoc of David and me in Austin. Justin is my student. Let me start. And whenever people have questions, please raise your hand virtually and ask them, or use any other method that G suggested. Okay. So the starting point of this talk is the great utility of randomness in computation. And this is a rather counterintuitive issue, because usually we don't leave decisions to chance. Usually when we have to make good decisions, we don't just toss a coin and decide according to the coin, but then somehow it turns out to be a rather fruitful thing to do for algorithms. And the idea is this: if there are many possible things you could do, and most of them would lead to a favorable outcome, then you might as well just choose at random what you do. And the rather counterintuitive phenomenon is that even in such a situation where almost everything you do is going to be fine, it might be difficult to point to one choice that is most definitely good. And that's why randomized algorithms sometimes outperform deterministic algorithms. And my favorite example is polynomial identity testing. So here's a problem. I give you this polynomial in polynomial formula in one variable, just like the one that's on the screen right now. And I ask you, is this an identity or not? Is this true for all x or not? And if you actually want to check it, you have to open all the parentheses. It's quite computationally intensive task. However, there is a very simple randomized algorithm, and the randomized algorithm says take x at random, say between 1 and 10 to the 10. The important thing is that it's the range should be sufficiently large with respect to 10, which is the degree of the supposed identity. So pick this random x, and then substitute x in the formula and check whether it holds or not. And this is an excellent algorithm because if this identity is false, then it could be true only for 10 different x's. So if you try much more than among much more than 10 possibilities, with overwhelming probability, you'll discover if this is false. And of course, if it's true, then you will always it will always check out to be true. Okay, so this is a great randomized algorithm. If n is the size of the circuit computing this identity and the degree is n, then this randomized algorithm runs in time order n or order n polylog n, depending on your computational model. But we don't have a good deterministic algorithm. The best deterministic algorithm that we know is substitute more than n points and check that it holds for all of them. And since substituting takes order n time, you need n squared time for the deterministic algorithm. And the really remarkable thing is that there is even a result that says that this gap is inherent to the problem. So Ryan Williams showed that under a certain assumption that he calls NSETH, any deterministic algorithm for checking polynomial identities takes at least quadratic time, n to the 2 minus some epsilon for every epsilon you want. So really, it looks like at least under this assumption, the best deterministic algorithm is n squared. The randomized algorithm is n. So there is this quadratic speed up by using randomness. Okay. On the other hand, we also have upper bounds on the power of randomization, and we've known that for 30 years now. So here is a result that I teach when I teach advanced complexity theory. This is one of the jewels of complexity theory. Under an assumption so there is an assumption here that I'm going to discuss in a second. Under this assumption, actually any randomized algorithm that runs in time t on input of size n can be simulated deterministically in times polynomial in t and in n. Okay, so this means that BPP, the class of problems with polynomial time randomized algorithms, is actually equal to p. Okay, the randomness doesn't buy you more than polynomial time. Okay, but it does buy you polynomial time. Right, so we saw this n versus n squared polynomial identity testing example, and okay, so let's talk a bit about the assumption, right? So it assumes that there exists a function in E, so that can be computed in exponential time, and cannot be computed by circuits. So here f is in E, but f cannot be computed by circuits that run in sub-exponential time. Okay, so if you have time, just say 2 to the half n, then you can do it with, even with circuits, right? So if we didn't have the circuits thing here, if it was just time 2 to the n versus time 2 to the less than 2 to the half n, then we have time hierarchy theorems, and we know that there exist functions that can be done in more time and cannot be done in less time. What makes this into an unproven assumption is that this talks about circuits. So even non-uniform algorithms cannot do it if they don't get enough time. Okay. Now this polynomial here, the running time of the deterministic algorithm, the exponent depends on this gamma. It's like at least 1 over gamma. So for the remainder of the talk, I'll consider an assumption where it's 2 to the n versus 2 to the gamma that is very close to 1. Okay, so we won't have this this blow up here. I mean, this is a completely reasonable assumption. As before, it's true if you didn't have circuits. With circuits, it's unknown but believed to be true. But even if you assume, you know, here this you know, even almost 2 to the n lower bound, still the running time here of the deterministic algorithm is going to be really large. So my collaborators actually checked in the most efficient construction here what would be the polynomial, and they came up with 16. We are going to talk during this lecture, we're going to talk about what are the sources of the large polynomial here, and there are big bottlenecks. There are big conceptual reasons why there is a large polynomial here. Definitely much larger than 2, right? We know because of this polynomial identity testing that we expect something like t and t squared maybe, but all the non-constructions have much higher polynomials here. Okay. Yeah. And this talk is about how we can get t squared here.
Sorry, Donna, one question. Say in this position, like what would you think the best you could possibly do in this?
T squared, right? Because of this polynomial identity testing. Well, the truth is probably t times n. We're going to talk about that. But definitely we have an example where the randomized algorithm takes time n, and the deterministic algorithm takes time n squared. So we don't think that we'll be able to do better than n squared unless we refute some big assumptions in complexity theory. But the question was whether we can get to n squared, to t squared here.
Sure. And do you conjecture that's possible, or is
so this is the theorem that we proved.
Okay, this is exactly what you're going to show. Sorry for stealing your thunder. Okay, go on.
Okay, so here is the theorem. So we have an assumption, and I'll talk about an assumption in a second. Let's talk about this. So any randomized algorithm that runs in time t on input of size n can be simulated deterministically in quadratic time. Okay. Notice that we take the maximum between t and n, right? We definitely know sublinear time algorithms that can run in extremely in time very close to constant, but definitely deterministically would at least need to look at the entire input. So this result is not about sublinear time algorithms. You should think of t, which is at least n, and then we can actually show that time t can be simulated in time, which is about t squared. So t squared plus something very small, arbitrarily small. Okay, so in this sense, this is a tight result. It behaves just like univariate polynomial identity testing. It shows that even for multivariate polynomial identity testing, where we actually don't have such a good deterministic algorithm, there should be a deterministic algorithm. Okay, but let's talk about the assumption. The assumption is what's written here in those first 2 sentences. We assume that there is a function that is computable in time 2 to the n on inputs of size n. And cannot be computed. So first of all, so we consider this time which is slightly below 2 to the n. This is what I said before, that we need to take this close to 1. But we also consider a stronger definition of circuits. Not only F doesn't have circuits of this size, but it doesn't have circuits that use non-determinism and randomness. So a circuit like this is actually a pair of circuits. The first circuit takes a witness and uses randomness and checks whether the witness is okay or not okay. And the second circuit, if the witness is okay, then it goes and computes the function. Okay? So this is this MA intersect co-MA model of circuits. And this little blurb that I had before mentioned that related and stronger assumptions actually appeared in the literature before. So, so there were papers that said, oh, let's assume, whatever we want, very strong assumptions, even stronger, higher in the polynomial hierarchy, and see what are the best results we can get. So we are very low in the polynomial hierarchy in what we assume, and this is a believable assumption that with less time, even if you have witness and randomness and non-uniformity, you won't be able to compute this function that really requires time to do the n. Okay, so under this assumption, we actually get the tight result. Okay. As I said before, I'd love to get questions, so please ask anything. Okay. So this is the main result of the paper.
How restrictive would you consider this? MA intersect co-MA. Should we think of this as being a minor restriction, or how serious is it?
I mean, it's all relative, right? So people considered, pseudorandomness researchers considered much stronger assumptions about models that are much higher in the polynomial hierarchy. This is low in the polynomial hierarchy. So it's weaker, and we think that this, we only say that this cannot compute. But it is a stronger assumption than the assumption that Impagliazzo and Vigdorsson had. And indeed, one of the open problems is, can you get rid of this, right? Sure. It would be nicer.
You conjecture so that you should be able to remove that?
Morally, yes, but we pushed the ideas we had as much as we could.
Sure. Bo Wagoner had the question, which he has posted in the chat. Do we know anything about converses to this result?
So this polynomial identity testing is a converse, but really, the exact converse. So this is a well-known open question in pseudorandomness, right? We know that circuit lower bounds imply derandomization. Does derandomization imply circuit lower bounds? And we don't have exact converses. We have, so there is the Impagliazzo-Cabanet's result that shows that some derandomization would imply some circuit lower bounds, but it's kind of a weird conclusion about circuit lower bounds. It's like an or conclusion. So in general, we don't have, even for Impagliazzo and Vigdorsson, we don't have converses. This is a wonderful open problem.
There's another question from Michel de R asking if AM cap co-AM is equal to MA cap co-MA.
No. Right, so here the randomness is only in the checking. There is no randomness in the computation of F, only in the checking of the witness. This is what this says. Any more questions? Okay, so let me continue. So I want to show you another result that we can prove. So this is about quantified derandomization. So let me tell you what's quantified derandomization. So this is a problem that Oded Goldreich and Avi Vigdorsson suggested a bunch of years ago, not that many years ago, and they were saying, okay, so we know by Chernoff that the error probability of any randomized algorithm can be exponentially small without loss of generality, right? But what if right, but this exponentially small error probability, if R is the number of random bits, maybe it's a 2 to the minus some constant R. It's definitely not 2 to the minus something very close to R, right? So suppose that you have an algorithm that really has an extremely small error probability. So the error probability is extremely small to 2 to the minus R. So here we have an algorithm that succeeds except on this many randomness strings. So this is a tiny error probability. Can you at least de-randomize those? Right, so this should be an easier task. And indeed, for this easier task, we're able to prove stronger results in two respects. One is that the simulation here is actually, the runtime is about t rather than t squared. Except that it requires some pre-processing of the hard function that we have. But this is independent of the algorithm. And any algorithm running in time t can be simulated in time which is about t deterministically. So this is one improvement. The other improvement is that the assumption no longer requires randomness in the checking of the witness. The checking of the witness is probabilistic, is deterministic, sorry. So for this easier derandomization task, we're able to prove stronger result. Okay, so these are the two results in the paper. And if there are no more questions, I'll start with the technical overview. Okay, so let's talk about how all those results get proven, and this is through this object called the pseudorandom generator. So a pseudorandom generator is this machine that takes a very small seed of true random bits and produces many bits, capital N bits, that are not random because they only depend on this seed that has many fewer randomized bits, but those bits look random to an algorithm. Okay, so this is what we want, that if we look at a circuit that is that has size just n, and I'm making the size of the circuit and the number of bits both n, just for simplicity. So for every circuit of size n that looks at those n bits, so they look completely uniform. So if you look at the output of the PRG when the seed is picked at random, and you see what's the probability that A says yes, it's about the same as the probability A would say yes on a completely random bits, okay, up to an epsilon. And this is exactly what we need for derandomization, because our circuit would be the algorithm that we're trying to derandomize, and the advice to the circuit is the input. So this defines the circuit, and then we want the algorithm to behave the same no matter if we give it the output of the PRG or completely random bits. And then all we need to do in order to derandomize is go over all possible seeds for the PRG and check for each whether the algorithm says accept or don't accept, and just do what the majority says. And if this works when you have uniform bits, it would also work when you have the output of the PRG. Okay, so this is the main paradigm for how we derandomize algorithm. This idea that what we care about is the strength of the beholder, of the randomness is in the eyes of the beholder. What matters is what's the strength of who's looking. So if you manage to fool the one who's looking, here the algorithm, then this is enough. Okay, and it derandomized. Let me say, for simplicity, think of epsilon, which is even like 0.9, and of course we do it for we construct pseudorandom generators for general epsilon, but large epsilon makes life easier. Okay, so all those constructions, the Nissan-Wigler zone and Impalazzo-Wigler zone and ours and other constructions I'll mention, all of them construct pseudorandom generators based on this hard function that we assume. Okay. Right, the number of seeds is the slowdown of the derandomization, right? Because we need to invoke the algorithm for every possible seed. Okay, so we want the number of seeds to be as small as possible, and the best thing we could hope for is that the size of the seed is logarithmic, and the question that we're asking is whether the constant of the logarithm can be 1 or not. Okay, so existing constructions in Palazzo-Wigler zone and so on have like a large constant here, which corresponds to the number of seeds being a large polynomial and the slowdown being a large polynomial. And if this is just 1, then the slowdown, the factor between the deterministic and the randomized would just be like linear in the number of bits we need, which is like linear in the runtime. Okay, so this is the question that we're asking. Can we construct this optimal PRG assuming a hard function? Okay, are there any questions about pseudorandom generators? Okay, yes. Pratik had a question.
Yes, so in that slide, what does the gamma mean over there?
Gamma is like so I use gamma of everywhere, right? Like here.
Yeah, it's the same gamma, okay.
It's the same gamma, right?
Right.
So gamma is like is here, and then I have gammas all over the place.
Okay.
Right? So this is like my slackness.
Okay.
So you don't expect to have exactly log n. You give yourself a little bit of slackness, and then you're going to, the runtime will be not, it won't be t to t squared, but t to the t squared plus gamma. Okay.
Yeah, thanks.
Okay.
There's another question from Varun asking, how does the epsilon in PRG affect the derandomization slowdown?
So, okay. There is, so we actually know what's the best seed size we can have, and there is a dependence in log 1 over epsilon. In log 1 over epsilon, or in 1 over epsilon. There is a dependence in 1 over epsilon. Yeah. So here, what we're doing is we take for ourselves this slackness here as the factor of the log n, and then as long as we work with epsilon, which is much larger than 1 over log n. I mean this is much larger than 1 over epsilon. The truth is, like, if you actually want the absolute right seed size with respect to the parameters, is you wouldn't have the order gamma here. You would have log n plus something that depends on 1 over epsilon. Okay, we just assume epsilon to be a very arbitrarily small constant, and then this is like way more than you need. Did this answer the question?
He said yes, thanks. There's another question from Stefide Agamule. I'm sorry for mispronouncing that. What if we use a non-uniform distribution if we care about some inputs more?
Wait, what if we use?
Like this is, I guess, staying close to uniform. Can you do things for non-uniform distributions?
So what you can do is, if you have a non-uniform distribution, you can always generate it with uniform bits. But our result works for uniform. I don't know if I mean, it sounds like an interesting, it could be an interesting follow-up work to say, oh, we actually care about, there are certain randomized algorithms that inherently use a non-uniform distribution. And then, right, so of course, you know, we can deal with those by using uniform bits to generate the new distribution, but then there is a loss, and you can bypass this loss by doing the same directly to this distribution of interest. So this could be an interesting, maybe follow-up work, but yeah, we don't do that. Okay, but as I said, the issue is that if you have a distribution which is not uniform, fine, you can still generate it with uniform bits. So this result still holds. Okay, did this answer the question?
I assume so.
Okay.
No further response.
Okay. Okay, so let's move on.
Sorry, there's one more question. Does it affect the size of the PRG? Is the question.
What's the size of the PRG?
Does it affect the size of the PRG?
What does?
But it's not clear to me what the it is here either.
Okay, I'll be happy to take this question later.
Yeah, maybe we can discuss this after the talk is done.
Okay. So right, all we're after is we take this hard function that we assume, and then we want to construct a PRG with optimal seed, with this seed. This is the point of this talk at the paper. Okay, so let me describe to you the methodology before this work. So this is what I used to teach in my advanced complexity theory graduate class. So first, use your seed to only construct one extra bit of pseudorandomness. Okay, and the very interesting observation of Sudan, Trevisan, and Vadhan from about, I guess, 97 it was, 20 years ago, was that this is actually equivalent to locally decodable codes. Okay, and this is something, right, the next slide will exactly explain that. And the interesting thing is that you can actually have small seeds as small as we want, just to generate a single extra pseudorandom bit. And the reason that there is such big loss is that we don't want just one extra pseudorandom bit, we want n pseudorandom bits. And to do that, there is this very nice methodology by Nissan and Vigilson with designs, and this is what uses the large seed. And this is where the problem lies. Okay, so what I want to do is I want to explain this connection between locally decodable codes and pseudorandom generators that output one extra bit, because this is going to be fundamental for this talk. And then I'm going to very briefly explain what was the problem here, why this required large seed, and not just this, other alternatives that people suggested required large seed, and then we'll talk about how we bypass those. Okay, so here is this Sudan, Trevisan, Vadhan, this conceptual, really interesting conceptual point. So suppose that you have a hard function f. We always assume that we have a function that can be computed in exponential time. Every bit can be computed in exponential time, but really requires exponential time. Okay, and we're going to instantiate it with inputs of size log n. Okay, where n is the number of pseudorandom bits we want. And this means that this truth table of this function is of size n. Okay, because it's like 2 to the log n, it's n. So we have this half function. It's a string of length n, and each bit, it can be computed in time n, and it really requires time, which is about n. Right? This is the half function. And what Sudan, Trevisan, Vadhan said was just take this and encode it with a locally decodable code. Okay, so I'll say in a second what a locally decodable code means. So the property is that if I give you a word that is sufficiently close to a code word, then, and you just want to decode a single bit here, then you can do that by making relatively few queries here, and overall running in time, which is much smaller than n. Right? So the idea is that before we had this n bits, and I mean, if there are no right, if there are no mistakes, then you can just, you want to read a bit, you can just, if you have it written down, you can just go and read it, and it takes constant time. And now you want to add resiliency to errors, right? So the new model is that you're going to get, you know, some of the bits here in the encoding are going to be ruined somehow, or going to be corrupted adversarially, and we still want to be able to decode individual bits here. But the point of locally decodable codes is that if all you want is a single bit here, you know, any of those, but just a single bit, then the runtime, you shouldn't have to go and read all of this and do an expensive computation on the entire supposed code word and decode all of this and then deduce the bit. But you can have sort of random access to bits here. So you can just read some of this and then be able to decode. Okay, so this is locally decodable codes. Okay. I'll be happy to answer any questions about locally decodable codes for those of you who see this concept for the first time. And the construction that STV suggested, yeah, and I should say they're actually extremely good locally decodable codes if you're willing that the runtime for computing a single bit would be like n to the alpha, say, where alpha is much closer, is much smaller than 1. Right, square root n, you know, n to the 0.1, whatever. You can actually do that with just linear length of the encoding. Okay, so in this sense, we have excellent locally decodable codes. What we don't know is how to construct locally decodable codes with constant number of queries and this length. But if you're willing to have larger runtime, larger number of queries, you can actually have very good length. Okay, so here is the construction of STV. Here is the way you generate an extra random bit. You use your seed to pick a random bit in the encoding of F. Okay, this is the extra bit that you choose. Okay, and you see that the number of seeds is exactly the length of the code. Okay, so if the length is linear, then the seed is logarithmic with constant 1 like we wanted. Okay. Okay, so why does this work? So here is the observation. Suppose that you had a circuit that knew that this was not a pseudorandom bit, so distinguish this from random. So what you have is actually this oracle access that lets you query a word that is non-negligibly half plus epsilon close to an encoding of F. Okay, but exactly the local decoding property tells you that even if you seriously damaged, you seriously corrupted the table here, and you only have half plus epsilon proximity to a code word, you can still decode any bit here in time much smaller than n. But the issue is that we know that bits here cannot be computed in time much smaller than n. They require time which is about n. Okay, so this is a contradiction. Sorry, this is a contradiction. So there cannot be A that distinguishes this bit from random. Okay, so this is this STV observation, how you can construct, how you can generate a single extra bit from locally decodable codes. This is a very important understanding for this talk. So if there are any questions, I'll be happy to answer them now. Okay. Okay, so let me move on. So I want to talk about the approaches that people had for generating more bits and why they didn't work. So one approach, the Nissan-Victor zone approach, said, okay, now we want n bits and not just one bit. So fine. So we need to use our seed to generate many bits. And they suggested to instead of choosing independent seeds, choose seeds from a design. I mean, this means something for some of you who already know this work. But the issue is that so what design does is that every two seeds here are mostly disjoint, are mostly on just independent, and this means that the length of the seed necessarily doubles. If you need to generate both, even just two of those, you need double the length of the seed, and we cannot afford double, right? We want 1 times log n, not 2 times log n. And you want to generate many, so you need a much larger seed overall. So this whole Nissan-Victor zone approach completely inherently has large seed. Okay. A different idea was by Shaltiel and Umans, based on work by Safra, Tashman, and Zuckerman, that suggested to use the Reed-Muller locally decodable code. And they noticed that with this, you can just, you can choose a seed and just choose a contiguous block. And if you look at the numbers, if you look at the actual parameters, you can only output like this square root n elements. This is by the definition of the Reed-Muller code. You just cannot output too many elements. So this is also you can't get, if you need n elements, you need a much larger encoding. Okay, so these were existing works, and this is the bottlenecks in getting n bits. There is actually another, in addition to those points, there is another very big conceptual difficulty, which is the infamous hybrid argument. So here is the hybrid argument. So suppose that you have this situation where you already know how to generate 1 bit and you want to generate n bits. Okay, so you want n bits that look like they're uniform. So look like they're uniform means that each bit has to look like it's uniform conditioned on all the previous bits. So each bit should be unpredictable to your distinguisher, to your circuit A, given everything that happened before. Okay, but you have n bits and you need it for all n bits. So there is a union bound that is going on here. So you need each bit to be, the error in the unpredictability should be 1 over n, because later you'll have n times that as the total error. And to get error per bit, which is just 1 over n, would require the length to be at least n squared. Okay, because the STV, the idea that I showed you, works when we want to generate one bit that is epsilon close to uniform, where epsilon is a constant. If epsilon becomes 1 over n, then at least you'll need the encoding of length n squared, a number of seeds, which is at least n squared. So there was a paper on beating the hybrid argument. This is something that people in the pseudorandomness community talked about, and they recognized as a major problem. Okay, so these are the main problems that were in getting like a good pseudorandom generators. The designs don't work, Ritz-Muller doesn't work, and the hybrid argument kills you. And each of them adds more and more factors to this polynomial runtime. Okay. Any questions? Okay. So there is this idea that was suggested before. So specifically in a paper by Barak, Shaltiel, and Witterzon, and this idea is that right, perfection is the roadblock to progress, right? So the entire point, what made this argument work, was that each bit was very close to uniform, and we tried all the n bits to be very close to uniform, and then you need per bit of 1 over n error. But suppose that you don't try so hard. You don't try to get a distribution that is really close to uniform, but you only try to get a distribution that just looks like it has entropy, right? So this corresponds to bits that are extremely low quality here. Not extremely, right? But pretty low quality. You don't want each bit to be unpredictable given the previous. You just want, in general, to have some entropy here. And the interesting thing is that if this is all you want, then you should be able to get it with a very small seed. A seed which is substantially smaller than log n. And then the idea was, okay, so do something like that, get those low quality, many bits, n bits, but low quality, and then use a randomness extractor to get from that actually bits that are close to uniform. Okay, and they noticed that this would beat the hybrid argument. Okay, and an extractor, right? We hope for an extractor that has seed length, which is about 1 times log n. So actually, you will use most of the seed for the extractor, and then little of the seed on the entropy generator, and this, at least you will get rid of the hybrid argument problem. Okay. So this idea existed. But then the issue is that it's much easier said than done, right? Conceptually, this is possible, but then the problem is that no one knew how to do that. So what you need for this thing to work is to be able to, to have this generator that generates n bits that are indistinguishable with bits that actually have mean entropy, which is omega n. Okay, if you actually had that, then this scheme could work, because we have extractors that have very small seed when the entropy rate is very large, is omega n. And the main issue is that if you have bits that are indistinguishable from bits with mean entropy, then definitely also the bits that you get here are indistinguishable, because if the bits here were distinguishable, this would also let you distinguish the bits here. Okay, right? So this is very nice. So right, this would have worked, except no one knows, not even us after this work, no one knows how to get bits that are indistinguishable from bits with mean entropy omega n. Okay, so this BSW, this is a paper that existed for a very long time now, and right, this was never implemented. Okay, if there are any questions, now might be a good time to ask. Okay. So what we do is we do construct this kind of entropy generator, right? So this thing is going to be the way we go. We try to generate bits that are low quality, using very low seed, but then we need to we do an extractor. So we are able to implement this framework. But the first issue is that we don't get bits that are indistinguishable from high entropy bits. We use a weaker notion of pseudorandom generator that I'm going to define next. So here is the notion. For every distinguisher, there should exist a distribution with high entropy such that the output of the generator is indistinguishable from truly from D. Okay, so I don't know if any of you noticed, but the difference between this and actual indistinguishability from high entropy is the order of quantifiers. Kind of the natural definition would be that there exists a distribution with high mean entropy such that for every distinguisher, the distinguisher cannot distinguish between the two of them. And we say something much, much weaker. For every distinguisher, there could be a different distribution that is indistinguishable. Okay? So this is a very weak notion of entropy. So Barak, Shaltiel, and Wigderson discussed this notion. This is a notion that was suggested by Omer Reingold. They call it metric entropy. So this is a possible notion. It's just that it doesn't quite work with the scheme, or at least prior to our work, it didn't seem like it works with the scheme that I suggested before. Okay, this could look kind of weird to switch the order of quantifiers and expect this to be a reasonable distribution. How come for every distinguisher there is a different distribution? How come this is natural? But in fact, I claim that this is an extremely natural, maybe the natural definition for entropy generator. And there is a picture that I really like that explains it, and this is this picture. So what this definition gives you is the following. Suppose that you have 2 to the r possible randomness strings, and among them there is a small set of size about 2 to the k, smaller than 2 to the k. Okay. Now comes the generator, and the generator doesn't look at all possible randomness strings. It only samples, it only looks at a few randomness strings within the 2 to the r. And therefore, in the PRG view, the situation can look completely different. It's possible, for example, that all the outputs of the generator completely fall within the set, right? Because there are very few of them. Or it's possible that many of them fall within the set and a few fall here. Okay, so it's possible. So here I draw another picture, which is what's the PRG view. If you only consider those points among the randomness strings that are outputs of the PRG, how does the ratio of this set look within this view? And what this definition talks about is about how much this can inflate. How much can this blow up? So it says that if you start with a set of only 2 to the k randomness strings, it can actually look like it's of, you can completely fall. All the outputs of the generator can fall here, or the view can be like this is on everything. However, if you look at a set that is smaller than 2 to the k, the PRG view is going to be smaller. It will still look small for the PRG. Okay. So to me, this is a reasonable definition of entropy. So you know, you have low quality pseudorandomness. So in you know, in true pseudorandomness, if this was the situation, then in the PRG view, this set should have been of the same fractional size. And in here, it's not of the same fractional size, but we have some upper bound on how much it blows up. Okay, if this is much smaller than 2 to the k, sorry, if this is much smaller than 2 to the k, then this is going to be much smaller than everything. Okay? Okay, so this is this equivalent definition, completely equivalent to this. For every distinguisher, the output of the generator is going to be at most a multiplicative factor. The true factor, and there is also an additive factor as usual. Okay. And the nice thing, one of the nice things about this definition is that this is exactly the definition you want if all you want is to derandomize algorithms that err early in this quantified derandomization setting. Well, the number of randomness strings on which you err is very, very small. All you care is that this won't become very, very large, right? So we want, if this was very small, then this won't be more than something like epsilon. And this definition guarantees you that. So pseudoentropy generator with this weak notion is exactly suffices for quantified derandomization. And through this scheme that I discussed before of first getting those low quality bits, pseudorandom bits, and then applying an extractor, it could be sufficient for the full thing. Okay. So I want to enumerate the contributions of this work and then tell you what I want to cover in this talk. And if you want to know more, you should just read the paper. So we have 4 contributions. The first contribution is that we point out that pseudoentropy generators, in the sense that I just defined for you, are actually equivalent to locally least recoverable codes. So if you remember STV, Sudan, Travis, and Vadhan, like 20 years ago, noticed that pseudo-random generators that output a single bit are basically equivalent to locally decodable codes. And here we say, if you want pseudo-entropy generators, so low quality, many bits that are low quality, this is actually the same thing as getting locally least recoverable codes. That is a notion that is considered and well known in the coding theory community. So this is this STV-like understanding. The second thing we do is we actually construct those locally least recoverable codes in the sense that we need here from locally decodable codes. Thirdly, so it was known that if you have n bits with omega n mean entropy, then you can actually use very small seed to extract. But we show that the same holds even when you have much less entropy. Even if you have n bits with just this amount, n to the 1 minus gamma amount of mean entropy, you can still use a very small seed to extract. And finally, we show that even though we only consider pseudo-entropy generators that are very weak, what I defined on the previous slide, you can still use any extractor you want to extract from them and get actual pseudorandom bits. Okay, so this is one of the things that BSW, so in this plan that BSW suggested, right, it wasn't clear that you can get that. We showed that you can get that. It wasn't clear that you can get that. We showed that you can get that, but in a weak way, it wasn't clear that the weak thing could be combined with an extractor, and we show that yes, it could be combined with an extractor without loss. So these are the 4 contributions of this work. And in this talk, in the time I don't have, I'm going to discuss just those 2. Okay, so
sorry, there was one question earlier, by the way, which I think it might have been earlier. Can the working of the PRG depend on A from Touchant-Mittal?
The working of the no. So the PRG, the PRG that we define works no matter what A is. Okay. I mean, we define one PRG, and now whatever A you give it, it's going to work. Okay, and it's going to work in this sense. The distribution is going to depend on A, but the PRG is uniform. Okay. So the convention I saw with previous Zoom talks is that it's okay to go over time because people can leave whenever they want.
Yeah, pretty much.
Are we going with that?
Yeah. So if people need to leave because they have another meeting at 2, well, it's 2 now, but we can keep going pretty much. No one's going to take our room.
Yeah. So I only have. I'm going to finish very soon.
Sure.
Okay, I just want to show you those 2 things, this STV, like instead of locally decodable codes, locally least recoverable codes, and instead of 1 bit, many bits, but low quality, and then how we construct those things. Okay. Okay, so let's talk about list recovery. Okay, so this is a notion that everyone who works in coding theory knows, but maybe people who don't work on coding theory may not know. So let's define that. So we have a code that takes n bits of information and gives m symbols of possibly a larger alphabet. Yeah, we think of a larger alphabet in this case. And the situation is this: so you have those n bits of information, and then you go and encode them with m symbols from this larger alphabet. And now what you're given is, per symbol, you're given a list of possible symbols in the alphabet. Okay, so you're no longer given just one word that is close to a code word, but you're just given those lists of symbols per coordinate. Okay, and we know something about the size of the list. The lists are relatively short, right? It's not all possible symbols in the alphabet. And the question is, can you still come up? So suppose that you know that there is a code word that where the symbol in the most of those symbols or many of those symbols appear in the lists. Okay, so within this list, for most lists or many lists, there is a symbol from the list that actually belongs to the code word. So under this situation, can you recover the code word? Okay, so this is list recovery. Okay, and then just like we had error correcting codes and then locally decodable codes, you can also define a local version of list recovery. And here you just want to know what's the ith bit of the code word, and you need to be able to do it in time which is much smaller than reading everything. So let's say much smaller than n. Okay, and as so this is the notion here. It's written according to this list decoding definition, which is what you need if you want the epsilon to be very small. I said in the beginning that we can consider epsilon which is very large And this corresponds to what's known in coding theory as unique decoding. And this means that you're in this easier situation where in most coordinates, the right symbol here appears in the list for almost all of them. And you just want to recover this word. Okay, so this is list recovery. You're given lists rather than giving a single one. If there are any questions about this notion, do let me know. I mean, one difference between local decoding as considered in STV and in here, and the way that coding theorists think about it, is we think of the decoder as a circuit. Okay, so we can hardwire to the decoder information about the word, the code word that we're trying to decode, but not much, because those circuits have to be of very small size, so they can't remember everything. We can't hardwire all the information about the code word. Okay, but it's a very similar situation for every bit here. There should be the circuit looks at is of size much smaller than n, and then is able to figure out the bit here. Okay, so this is list recovery. Now we're going to consider a twist on list recovery. And the twist is that we're going to consider it in a regime of parameters that coding theorists usually don't consider. And this is the following regime of parameters. So usually the way coding theorists think about it, you have n bits of information, you encode them with m bits, m which is about n, and the alphabet is a large constant. Okay, this is standard, and then the list size is constant. What we want to consider is an incredibly large alphabet. So the alphabet, log the size of the alphabet, so the number of bits that are required to write a symbol here, is going to be almost n. So n to the 1 minus gamma. And then m is going to be about n to the gamma. Okay, so this is a very weird regime of parameters for coding theories, but completely legitimate. So there are few symbols, just n to the gamma symbols, but each one requires almost n to the 1 minus gamma number of bits. Okay, so the alphabet is huge, and the list size are appropriately huge. So they're going to be, so the list size is going to be much smaller than the alphabet, but still 2 to the n to the 1 minus gamma. Okay. And okay, and somehow we want to work with this, and notice, right, we still want the circuits to work in time in size that is much smaller than n. Okay, so the circuits, the decoding circuits, actually don't have enough time to read the entire list. Okay, so when coding theory people think about this problem, they usually, the first thing is like you read the entire list. And here you cannot read the entire list because the list is huge. But the way we kind of, the one thing we do give the circuits is we let them use nondeterminism. This is where nondeterminism will get into our result. Okay. So here is what you can do, how you can access a huge list. So I wrote here that the alphabet again is of size which is exponential, like 2 to the n to the 1 minus gamma. So the alphabet is huge. Recall that we want to work, the decoder needs to work in time which is much smaller than n. Within this large alphabet, there is a list. I'm denoting the size of the list in 2 to the k. K corresponds to the entropy that I'm going to get. We'll see it later. But the list size, let's say, is 2 to the k. And we think of k as also of size n to the 1 minus gamma. And what we're given with this list, we're given membership oracle, right? So we are able, so right, it's huge lists, but given a string in this, we are able to tell whether it's in the list or not in the list. So this is what we're going to assume on the lists. Okay, we're not going to read the entire list. We're just going to be able to check membership. And notice that checking membership, since this is something on n to the 1 minus gamma bits, I mean, this is something you can do in less than n time. Okay, so we have this. So this is the situation that we have. The circuit has, though, a non-determinism that it can use. And this is what we do, right? The standard theoretical computer science approach of hashing. Okay, if the list is of size 2 to the k, and we know this bound on the list, we can just hash everything to a range of size 2 to the k. And then what we can do is get, so we have this long list. We can just ask to hardwire the hash of the of the true symbol from the list. We're going to ask to hardwire it to the circuit. And the issue is that k is only of size which is much smaller than n. So I mean, it's a fair game to hardwire a string from here. And given this hardwiring that tells us what is the correct element in the list, now we can use non-determinism to guess what's the right element in what's the right symbol, and then we can check that it indeed hashes to what we were hardwired, and indeed that it's also in the list. Okay, so the situation is in this list recovery. So those lists are huge. We can't read all of them, but we have this mechanism that I just showed you that is able to take a list and tell us what's the right symbol from the list that should go here, right? And the issue is that n, the number of possible symbols, is just n to the gamma. N to the gamma is tiny, so we can hardwire for each one of those coordinates. We can hardwire to the decoder what's the right symbol from the list if the right symbol is in the list. Okay, so this is the situation that we're in. Okay, so this is local list recovery, and I want to show you why pseudoentropy generators follow from locally list recoverable codes in this sense. So suppose that you have, it will be like an STV type construction. Suppose that you have your hard function f, and then you encode it with a locally list recoverable encoding. So each one of these is an alphabet symbol. We call it, it's a large alphabet, and each alphabet symbol has many bits. So these are the different symbols. And the seed is just going to choose one symbol from the alphabet, one symbol from the encoding, and this is what the generator is going to output. So this is the construction. And the claim is that just like with STV, this is exactly a pseudoentropy generator. And the idea is that if this weren't an entropy generator, then there should be an A that corresponds to a very, very small set, a set of size much smaller than 2 to the k, that somehow captures lots and lots of those symbols. At least epsilon fraction of the symbols are within A. And what we said is that right, if this is the situation, if we have lists that for epsilon fraction of the symbols, the symbol is in the list, then we should be able to decode each bit here with a size that is much smaller than n, but we know that we can't, because this is a hard function, and therefore this does not exist. Okay, so this must be an entropy generator. Okay, so the observation is that locally least recoverable code is exactly right. So this set that expands a lot, right? If this is not an entropy generator, exactly corresponds to lists for those coordinates of the code word. Okay, so yeah, question?
There's a question asking, does your non-determinism hardness assumption correspond to the large lists for which you need to guess the hash?
Yeah. So the non-determinism comes from here. We use non-determinism to be able to access the list. Okay, so the algorithm, the circuit that we're getting to get the bit here uses non-determinism to access the list, and that's why it's non-deterministic. Okay. Yeah. So yeah, a pseudoentropy generator is basically the same thing as a locally least recoverable code. Yeah. So this is right, the first conceptual understanding of this paper. Still, it wasn't clear how you construct those least recoverable codes, especially because everything that is known and is done by coding theorists is for a completely different regime of parameters, and they always assume that the alphabet is a large constant and you can read the entire list, and we cannot assume this. However, we do work in this easier setting where we have non-determinism and advice, and we can hardwire the information about the code word. So here is the construction. The construction ends up being very simple. You take your hard function, say, right, recall that we think of the truth table as of size n, and then we take a locally decodable code, just a normal locally decodable code of encoding, and use it to encode f. We take the alphabet size to be sufficiently large with respect to 1 over epsilon. And now we take this completely general locally decodable code, and we partition it into n to the gamma blocks of size n to the 1 minus gamma each. And our seed just goes and picks a random block. Okay. And the point is, right, so this is a good least recoverable code because this is a good list, because this is a good locally decodable code. Okay, so we are in this situation where even if we have those lists, we are able, at least for epsilon fraction of them, to get the correct bits here. And if we have for epsilon of the blocks the correct bits, then the locally decodable code with the large alphabet should be able to allow us to decode any bit here. Okay. Yeah, and I should say the original construction that we had took a locally decodable code, a binary locally decodable code, and then created those blocks with an expander. And then Noga runs Evie noticed that we could have just even done this much easier, arbitrary blocks from a locally decodable code of large alphabet. Right, but yeah, question? Is there a question?
Yeah, there's one question from Tushant Mittal asking, does the fact that circuits use non-determinism lead to the milder assumption that F is hard to compute using non-determinism and not randomness, i.e. the n cap
so so if we return to the main, so what I showed you so far was how to prove this, right? If you only want to quantify the randomization, so you just want a pseudo entropy generator, you just don't want small sets to expand, Right, so this is the result I showed you. You can use a very, very small seed, right? Because the length is really small, the number of blocks is very, very small. So this just corresponds to this, and the runtime is this. But you need non-determinism in order to query the lists. So this corresponds to the assumption here. Okay. So what I showed you so far, this is the only thing I want to show you. I mean, I just finished the technical content of this talk, right? We just proved this theorem. Okay, and the huge lists lead us to use non-determinism and require this stronger assumption, and the small seed corresponds, the extremely small seed corresponds to a very small runtime here. Now the reason we need MA intersect co-MA, this is actually because of the extractor, of applying the extractor, that, as I said, was completely unclear that you should be able to apply an extractor with such a weak notion of entropy, and we showed that you can, but then you need randomness. So this is what leads to this stronger thing, and the extractor also needs more seed, and this leads to the larger runtime. Okay. Yeah. So this is the result. These are the results of the paper. As I said, I only covered those two. The pseudoentropy generators are the same as least recoverable, locally least recoverable codes, and what's the construction of least recoverable codes. And I didn't talk about the extractor part at all. Yeah, so this is it. This is what I wanted to cover. I just want to end with some of the many open problems. One of my favorite open problems is that the truth might be that if you have a randomized algorithm that runs in time t on inputs of size n, that maybe you should be able to simulate it deterministically in time tn and not t squared. So in the polynomial identity testing problem, t was equal to n, and so t squared and tn were the same. But in general, t could be much larger than n, and this could be much smaller than t squared. We're not able to do that. One of the things you will have to do that is, so I think someone asked me during the talk whether the pseudo-random generator depends on the algorithm that we're trying to fool or not. And I said, no, we have a pseudo-random generator that works for any algorithm. But if you want to achieve this, what you need to do is get a pseudo-random generator that works against a specific algorithm, but with all to the n possible inputs. And we're unable to do that. This is a wonderful open problem, and this was probably the right answer. Okay, so this is the first open problem I want to suggest. This is a problem that Liji Chen and Scott Aronson independently, each of them, as soon as they saw this result, they asked about this. So they came up with this problem. Okay. Second question. When we talk about small complexity, small circuit classes, we actually have unconditional pseudorandom generators. Those pseudorandom generators have horrible seeds, and it would be very interesting to try to get optimal seed, unconditional, against constant depth circuits. This also seems hard, especially since it's not clear that you can use, suddenly you can't use non-determinism, because if you add non-determinism to all those constant depth circuits, you actually get NP. So you can't just assume things about non-determinism. You need to do something more refined. Third problem, we didn't get the optimal parameters. For example, our pseudoentropy generators only outputted a mean entropy, which is n to the 1 minus gamma instead of omega n. It would be interesting to output more entropy. And in general, remove non-determinism from the assumption, or remove MA intersect co-MA from the assumption would be very interesting. Yeah, so these are the open problems, and this is it, and I'm happy to take questions.
Thank you very much, Donna, for the excellent talk. Yeah, in terms of questions, actually there was a follow-up to the previous one, which I missed. Tushant is asking, can you explain why there's a co-NP in the assumption?
So the fact that it's a, so let me scroll back to the main theorem. The fact that it's NP intersect co-NP, right, this is an advantage, not a disadvantage, right? Because what we want is to put here the smallest complexity class that we want, that we can, right? So in Pagliazzo-Wigder zone have basically P here, right? So P circuits, or like P/poly circuit. Or it's not P, right? It's this size, right? It's a sub-exponential, but they have like just a normal deterministic circuits, and we want to put here the lowest thing we can have. So the fact that we have NP intersect co-NP is good. The reason, I mean, there is no asymmetry. If you just talk about NP, then there is this asymmetry where for the one inputs you are able to use the witness, for the 0 inputs you are not able to use the witness. And here there is just no difference between 0 and 1, right? If you look at our scheme, we are able to decode the right in the, where was it? We are able to decode the bit here, no matter if it's 0 or 1. We need non-determinism and we need non-uniformity to be able to access those huge lists that we have. But once we use non-determinism and non-uniformity, we're able to decode the bit no matter if it's 0 or 1. There is no asymmetry. Okay?
There's a question from Shruti Shekhar, which asks, which extractors do you use on top of this weak pseudo-entropy generator?
So it's extractors from this work of so the important thing is the parameters, right? So we want to use the optimal seed, essentially optimal seed 1 times log n extractors, and they need to output from pretty high entropy. And we use extractors from this work of David and I think Amnon and Chris, sorry, Amnon and Muli Safra, right? It's one of the papers I mentioned, and we show that we can adapt them to work with pretty low entropy and still have very good seed. And you can read, right, if you want to know those, you should go and read their paper. It's in the appendix, I think. Oh, maybe in the full version, it's in one of the chapters. There is a whole construction. It's not, right, it's a somewhat complicated construction. It's a construction of the sort that people in the extractor community have. You divide to blocks and then you extract from blocks, from block source. Yeah. More questions?
All right, are there any more questions? At this point, you can definitely feel free to just unmute yourself and ask.
Hey, Donna. I have a question.
Mm-hmm.
I just want to get a feeling for this MA intersect co-MA assumption. What other results depend on assumptions similar to those?
So I think that there was a paper, I think of Salil and Luca, that talked about go higher in the polynomial hierarchy. They go much higher, and then they get some generators. I don't even remember what was the motivation now. I don't remember what was exactly the result that they wanted to achieve. I used to know it.
But they get some sort of pseudorandom generator as well.
They get pseudorandom generator. I wonder if it's under non-uniform assumptions. Yeah, I don't remember. Oh, yeah. Also, Chris and Ronen also. So they talked about derandomizing. Oh, if you want to derandomize AM, then you would use assumptions about non-determinism. So Chris and Ronen definitely have those assumptions. I think that these are the two main papers that use those assumptions. One, I think, by Salil and Luca, and one by Chris and Ronen. You would say that the Chris and Ronen paper, if you want to derandomize AM, you have to assume something about non-determinism. So it's less surprising. And maybe the other application, it's more surprising.
Do you think you could use your techniques to also derandomize like AM?
Probably. Right. So the general understanding in the pseudorandomness field is that just like you can derandomize, you can prove BPP equals P under hardness assumptions, you can also prove AM equals NP under hardness assumption. The only works I know about it are by Chris and Ronen. Right. I haven't checked that the same thing works, but my feeling would be that yes, you should be able to extend.
Cool. Thanks.
Okay, more questions.
Right, more questions? There is a question from Samuel McGuire, which is kind of long, but I'll read it out. Per your paper, one way of framing the use of non-determinism is converting Yao pseudoentropy to metric pseudoentropy. Have you thought about different notions of pseudoentropy to start with that might not need non-determinism to do the conversion to metric pseudoentropy? One that comes to mind is the dense model theorem, which is that your distribution is dense inside of a pseudo-random set.
Yeah, so the dense model theorem has inherent losses that just make it useless for us. You cannot have small seed with the dense model theorem. But other than that, yes, it could have worked. Yeah, I kind of on purpose I refrain from talking about Yao entropy and metric entropy and all those names, because I mean they confuse me. So I only discussed this the notion that we consider the exist for all, the for all exists, as opposed to the right, which is this is metric, as opposed to exist for all, which is Yao. Yeah, but yeah, no, we thought about different notions of entropy, and this is what we came up with. We think that this is the right way to do it.
Thanks from Sam. Any more questions? If not, I'll take a sort of off the air, and then people can ask more questions that they're too shy to ask on air. But I just want to remind you that, well, first of all, thanks again, Donna, for giving a great talk. Next week, we'll have Venkat Guruswamy presenting, and then we'll have talks every week after that until going all the way to May. So yeah, please check out the website for more information. Thanks for joining us.
Thank you.